Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
NASA's James Webb Telescope has been an astonishing piece of technology for the advancement of humankind's understanding of the universe, and the source of awe-inspiring images of black holes, galaxies, and nebulae. It's returned to scientists and astronomers since it was deployed into a solar orbit back in 2022. At this point, astronomers are used to James Webb pushing the boundaries of astronomy. So it is little surprise that the $10 billion telescope has surpassed itself again. According to the latest update, the Webb telescope might have detected a new wow signal from Proxima Centauri, the closest known star to our solar system. This discovery, if verified, would be nothing short of revolutionary, suggesting the existence of artificial structures or civilizations beyond Earth. But how credible is this claim? Could it be that humanity was on the verge of confirming the existence of intelligent life beyond Earth? All this and more will be discussed in today's episode. Proxima Centauri, a red dwarf star located just over 4 light-years from Earth, holds a special place in our understanding of the cosmos due to its status as the closest known star to our solar system. However, despite being the closest star to our own solar system, it is too dim to be seen by the naked eye and was not discovered until 1915. This finding made a significant moment in astronomy, as this faint star revealed hints of other worlds beyond our own. The Proxima Centauri system is fascinating, especially because of its known exoplanet, Proxima b, which was discovered in 2016. Proxima b orbits within what is known as the habitable, or Goldilocks, zone of Proxima Centauri. This zone is crucial for the potential existence of liquid water, because temperatures within this region could, in theory, allow water to form and remain in a liquid state on the planet's surface. Finding a planet in the habitable zone around any star sparks curiosity about its potential for life. Proxima b in particular has garnered a great deal of interest due to its location in this zone, which raises intriguing possibilities about whether it might sustain conditions suitable for some form of life. The warmth that Proxima b receives is a result of its proximity to Proxima Centauri. Unlike Earth, which is located about 93 million miles from the Sun, Proxima b is situated at only about 5% of that distance from its host star. This close orbit causes Proxima b to complete a full revolution around Proxima Centauri in just 11.2 Earth days, a stark contrast to our own 365-day year. This rapid orbit is characteristic of many exoplanets around red dwarf stars, which often have tight, short orbits due to the star's relatively lower masses and gravitational pulls. The planet's close proximity to its parent star gives it a warmth that, if conditions were favorable, might support liquid water. A tantalizing prospect for astronomers hoping to uncover evidence of habitability beyond Earth. While Proxima b's placement within the habitable zone seems fortunate, this position comes with significant challenges. Orbiting so close to Proxima Centauri subjects Proxima b to intense levels of radiation and a barrage of charged particles. Red dwarf stars like Proxima Centauri are known to be highly active, frequently emitting powerful solar flares that can release massive amounts of radiation into nearby space. For Proxima b, this activity means it is regularly bathed in radiation levels far beyond what Earth experiences from the Sun. This radiation can strip away planetary atmospheres, creating an environment hostile to life as we know it. NASA studies suggest that even if Proxima b once had an atmosphere similar to Earth's, the intense stellar radiation would erode it relatively quickly. Models indicate that Proxima b's atmosphere, if it existed, would be blown away in approximately 100 million years. Without a stable atmosphere, Proxima b would lack critical protection from space radiation and would be unable to sustain surface water or any Earth-like life. an atmosphere provides a protective shield that helps to regulate temperatures and supports various processes, essential for sustaining life. On Earth, our atmosphere enables complex weather patterns, shields us from harmful ultraviolet rays, and traps heat in a way that supports life across diverse ecosystems. However, the absence of an atmosphere on Proxima b severely limits the chances for life as we know it to survive. Proxima b's environment illustrates some of the unique challenges faced by planets orbiting red dwarfs. While red dwarfs are the most common type of star in the galaxy, their frequent solar flares and intense stellar winds pose formidable obstacles for habitability. The powerful flares can drastically alter planetary atmospheres, and for planets like Proxima b that orbit within such close proximity, the conditions become particularly extreme. This harsh environment would create conditions hostile to most known forms of life, especially complex organisms. However, scientists consider the possibility that simpler, resilient forms of life could adapt to such harsh settings. The concept of extremophils on Earth offers a glimpse into how life might survive on Proxima b. Extremophils are microorganisms that live in environments once thought to be uninhabitable, such as deep-sea hydrothermal vents, highly acidic hot springs, or radioactive wastelands. These organisms have evolved unique mechanisms to withstand conditions that would be lethal to most other life forms. On Proxima b, if life were to exist, it might look more like these extremophiles, capable of surviving in highly radiated environments, perhaps by hiding in subsurface regions or using biochemistries resistant to radiation. Moreover, on Earth, certain types of extremophiles are known to thrive in environments with minimal oxygen, high salinity, or extreme temperatures. Similarly, life on Proxima b might rely on unconventional metabolic processes, possibly using chemicals in the planet's soil or, if water is present beneath the surface, in underground water reserves as sources of energy. This would be a form of life that fundamentally differs from the life forms we know, possibly lacking the need for sunlight or even relying on chemical energy rather than photosynthesis. If life did develop on Proxima b, it could also have adapted mechanisms to repair DNA damage caused by radiation, similar to certain Earth bacteria found in radioactive environments. Some organisms on Earth have developed the ability to repair DNA at rapid rates, allowing them to survive and even thrive under conditions that constantly damage their genetic material. The debate about the possibility about life on Proxima reached the peak when the Breakthrough Listen project, a privately funded initiative dedicated to searching for extraterrestrial signals, detected a peculiar radio signal while observing Proxima Centauri with the Parkes Radio Telescope in Australia in April 2019. This signal, dubbed BLC-1, Breakthrough Listen Candidate 1, was intriguing due to its narrowband nature at around 982 MHz, a frequency not commonly used by human-made devices or known astrophysical sources. The uniqueness of the frequency range suggested it might not be interference from typical Earth-based signals. Adding to the mystery was the fact that BLC-1 exhibited a frequency drift, which suggested it could be coming from a source moving relative to Earth. Such drift is commonly associated with signals from space-based objects rather than fixed terrestrial sources. The combination of these features, a narrowband signal at an unusual frequency with frequency drift, sparked excitement and speculation about the possibility of an artificial extraterrestrial origin. And the fact that this mysterious signal came from the direction of our closest neighboring star system only added to the excitement. However, scientists were cautious from the beginning. In the field of the search for extraterrestrial intelligence, also known as SETI, there have been many false alarms. Signals detected in the past have often been traced back to human-made interference, and it's a constant challenge for SETI researchers to distinguish between legitimate extraterrestrial signals and radio interference originating from Earth. A true signal from an extraterrestrial civilization would have a narrow bandwidth, show amplitude or frequency modulations. Providing information, it would be seen when looking at a target, and it would never be seen when looking away from the source. We have seen tantalizing hints of alien intelligence before. On August 15, 1977, astronomers at the Big Ear Telescope picked up a 72-second signal that showed signs it was broadcast by an intelligent alien civilization. However, this wow signal never repeated, and so could not be confirmed. So, did we really detect an alien message form, Proxima Centauri? Could it be that humanity was on the verge of confirming the existence of intelligent life beyond Earth? These questions took a dramatic turn with recent stunning observations made by James Webb. With its large, segmented mirror and ultra-sensitive instruments, James Webb can detect faint infrared light from distant exoplanets, allowing astronomers to study their atmospheres, temperatures, and surface conditions. It was designed to look for biosignatures, indicators of life such as oxygen, methane, or water vapor, but its precision has led to speculation about whether it might also spot technosignatures, indicators of advanced civilizations, such as artificial light or radio signals. As a result, James Webb has already captured the most detailed images of Proxima b yet, peering through the haze of its atmosphere, if it has one, and even analyzing the heat distribution across its surface. But one of the most surprising revelations has come from its observations of Proxima b's night side, the side that is always turned away from its star due to tidal locking, a phenomenon where one side of the planet permanently faces the star, while the other remains in perpetual darkness. And here, what James Webb found has sparked intense debate in the scientific community. According to some interpretations of the data, the Webb telescope detected unusual light emissions coming from the night side of Proxima b. These emissions were not consistent with natural phenomena like volcanic activity or auroras, leading some researchers to hypothesize that they could be the result of artificial lighting, similar to the city lights we see on Earth when viewed from space. At first glance, this idea seems far-fetched. How could a space telescope located millions of miles from Earth possibly detect something as subtle as city lights on another planet? The answer lies in the unique capabilities of James Webb's infrared sensors, which can detect even faint energy emissions across vast distances. The light observed on Proxima b's dark side reportedly showed a regular, grid-like pattern, which would be unusual for any natural process, but highly indicative of structured artificial sources. If this pattern truly represents city lights, it would be one of the most groundbreaking discoveries in the history of space exploration. Detecting such signals would imply a level of technological advancement on another world, hinting at the existence of an intelligent civilization. This discovery would profoundly impact our understanding of life in the universe and raise profound questions about the nature, culture, and even the intentions of other civilizations. Even just identifying specific patterns in Proxima b's atmosphere or surface that suggest industrialization or other human-like activity would change our perspective on being alone in the universe, ushering in a new era of exploration, diplomacy, and scientific inquiry. However, verifying something so distant and interpreting it accurately remains challenging. We'd need significant follow-up to confirm any evidence. And of course, Proxima b is just one among many promising candidates with conditions that might be favorable for life. Scientists recently discovered one particular source of flashing light has already proven especially puzzling. It blinks about once every 22 minutes, and according to archival data, it's been doing that at least since 1988. It's called GPM J183910, and scientists concerned they might have picked up a message from a distant alien civilization. Observations show this impossible spinning object releasing a giant burst of energy 3 times an hour. And when astrophysicist Dr. Natasha Hurley Walker discovered it, she broke out in a cold sweat. The most obvious analog for GPM J0183910 is a pulsar, a rapidly spinning magnetized neutron star. These objects release radio energy at their magnetic poles, which may not be lined up with their axis of rotation. As a result, the star's rotation can sweep the poles across the line of sight to Earth, creating the perception of a flash of radio waves each time one of the magnetic poles aligns with Earth. But the flashes of pulsars repeat quickly, with a gap between them of anywhere from around a minute down to milliseconds. And, more significantly, physics dictates the gap has to be quick. The magnetic field that powers the production of radio waves is generated through the star's rotation. If it starts rotating too slowly, then the magnetic field will drop to a point where it can no longer generate significant radio emissions. In other words, if it slows down, it goes dark, which is why we don't see any that take much more than a minute between pulses. That doesn't rule out neutron stars, though. Another option involving them is the magnetar, a neutron star with an intense magnetic field that's prone to energetic outbursts. But those outbursts also generate more energetic photons, and the researchers checked the site of GPM J0183910 with an X-ray telescope and saw nothing. Plus, magnetars are thought to rotate more quickly than the 22-minute gap implies, so they're probably out as well. Another alternative is a white dwarf with an unusually strong magnetic field. These are much larger objects, and so take a lot longer than a neutron star to rotate. But we've observed thousands of them within the Milky Way and haven't seen anything like this. There's only one with periodic emissions, and it outputs far less energy than GPM J0183910. Even if we expand the list of potential sources to include other objects we don't understand, we still come up short. The same team had identified another slow-repeating radio transient, Galeem X J1627595523504.3, a few years earlier. But it was only active for about 2 months before fading from sight, a far cry from the 35 years that GPM J0183910 has been bursting. So, given that every possible explanation is terrible, where do we go from here? The good news is that these objects will be so difficult to spot that it's possible there are a lot more out there that we've overlooked. The bad news is that they're still hard to spot. The length of the burst, up to 300 seconds, and the gap between bursts means short cadence observations will likely either see something there the whole time or miss it entirely. We'd really need to have hardware stare at a single area of space for a half hour or more, and to have it staring divided up into multiple exposures, to be sure we catch it in both its on and off states. And that involves a major commitment of hardware. In the meantime, we can potentially narrow down the location of GPM J0183910 to try to see if there's anything interesting in other wavelengths. However, since this is located within the galactic plane, that's going to be challenging as well. Regardless, what's notable, Dr. Hurley Walker's not quite a close encounter is not the only clue that we might not be alone in the universe. Harvard University astrophysicist Avi Loeb has made breakthroughs in research on black holes and the early universe. But he is also fascinated by the possibility of life on other planets. He had worked on a project to send laser-powered spacecraft which use thin mirrors called light sails to explore nearby stars. But in late 2017, astronomers spotted a visitor from another star pass through our solar system. The object was named Oumuamua, a Hawaiian word approximately meaning scout, by its discoverers. Early studies of the object raised questions as it had characteristics which were difficult to attribute to natural causes. Its shape was described as a 100-meter-long cigar or pancake, and it bore little resemblance to any known comets or asteroids. Oumuamua also appeared at least 10 times more reflective than rocks usually seen within our solar system, which, to some, suggested the shine of polished metal. And bizarrely, as the object passed by the sun, it zoomed off at a speed faster than could be explained by the star's gravity by itself. This observation particularly then caught all scientists' attention, as it hinted at the possibility of outgassing, a phenomenon common in comets where volatile materials sublimate and create jets of gas that propel the object forward. However, no such outgassing was observed in Oumuamua's case, deepening the mystery. The majority of the scientific community favors natural explanations for Oumuamua's unusual characteristics. One leading theory suggests that Oumuamua is a fragment from a larger body that was torn apart by tidal forces during a close encounter with a star. This fragmentation could explain its elongated shape and rapid rotation. Another theory posits that Oumuamua is a comet, with outgassing that is not directly observable from Earth. This outgassing could result from the sublimation of volatile materials on the surface of Oumuamua, providing the necessary thrust to explain its acceleration. However, the absence of a visible comet-like tail or coma challenges this explanation. Additionally, some astronomers propose that Oumuamua could be a hydrogen iceberg. In this scenario, the object is composed of solid hydrogen, which sublimates and provides the acceleration force when it gets close to the Sun. This theory is particularly compelling to me because it would imply the existence of a population of hydrogen icebergs in interstellar space, a phenomenon that has not been considered before. However, this idea is not without its challenges, as the survival of a hydrogen iceberg on a journey through interstellar space raises questions about its origin and the conditions required for its formation. Despite the array of natural explanations, the notion that Oumuamua might be an artificial object, an alien spaceship, has gained traction in some circles. Prominent among its proponents is Avi Loeb, who has argued that it was obvious that the object was in fact a derelict and abandoned light sail, like the kind he had been working on, made by a now extinct galactic civilization. He was so convinced by his hypothesis that he published a paper in late 2018 with co-author Shmuel Bialy, a Harvard postdoctoral fellow, stating that the object was humanity's first contact with an artifact of intelligent extraterrestrial origin. According to Loeb, a light sail is just like a sail on a boat that reflects the wind. The wind is pushing it. In the case of a light sail, it's the light reflected off its surface that gives it the kick, the push. Light is made of particles called photons. The red-tinged rock was estimated to be possibly 1,300 feet long and zooming away from the Earth and Sun at more than 16 miles per second. Avi Loeb then even published a book on January 26, 2021, which contained details that support his claim that Oumuamua was an alien light sail. According to Loeb, even if you consider a razor-thin piece of paper tumbling in the wind, the amount of area that is projected in your direction is not varying by more than a factor of 10, because the chance of seeing it edge on is really small. It is tumbling in the wind, so it looked like this object has an extreme geometry. Despite the fact that Loeb continues to make headlines with his assertions, the copious flaws of his analysis render it thoroughly unconvincing to all but the most uncritical onlookers. After all, it's very clear that whatever the true nature of Oumuamua is, it's unlike any other object we've ever seen. There has since been a second interstellar object observed to enter into our solar system, but that one was large, volatile-rich, and comet-like, and which never approached particularly close to the Earth. There are clearly large populations of objects that originate from other stellar systems traversing the interstellar medium, and it's eminently probable that as our observational capabilities improve, we will begin accumulating large sets of data about the types of objects that pass through our solar system, despite originating elsewhere in our galaxy. With superior data coming once the Large Synoptic Survey Telescope at the Vera Rubin Observatory coming online, we may soon have a much more definitive picture of precisely what's out there, flying through the Milky Way's interstellar space. Put interstellar visitor aside, don't you know that astrophysicists were left baffled after the most mysterious star in the universe was in 2015, sparking a huge scientific debate due to its dramatic dips in its brightness? The star is officially called as KIC 8462852, but was named Tabby's star after Dr. Tabitha Boyajian, who first discovered it. Tabby's star has a combination of properties that make it entirely unique. All at once, it exhibits huge drops in its flux by up to 22%, while most planets cause 1% dips, fades slowly over timescales of decades with occasional brightening events, which no other similar stars are known to do, where the overall brightness fluctuates around the dips, rather than the smooth decrease and increase seen for planets, but with no infrared emission, which all other stars with large flux dips possess. This created a huge puzzle. It couldn't be planets, because no planet is large enough to block that much light from its star. Even if you envision a planet with an enormous ringed system, like a super Saturn, those flux dips would be both periodic and exhibit a smooth pattern with a plateau. This contradicts the available data. This could have been a very young star, with planetesimals, a proto-planetary disk, and an extremely dusty environment. We've seen stars with large flux dips around them, and they've all fallen into this category. But Tabby's star is much too old to have a protoplanetary disk, many hundreds of millions of years too old. It also, most importantly, doesn't exhibit the infrared flux emission that a star with a protoplanetary disk ought to have. This is why the star was originally named the WTF, for Where's the Flux star. It could be a series of cometary events where they emit large amounts of dust being kicked up as they infall onto the inner portion of the solar system in question. This could, as was shown relatively recently, explain the short-term flux dips that have been seen. But there's another phenomenon that this proposed solution cannot account for: the long-term dimming of the star. This star isn't called Tabby's star or Boyajian's star because it was discovered by that particular scientist, only because she led the scientific investigation concerning the interesting and important new behavior. But this star has been known for over a century, and observations indicate a long-term fading, which this model cannot account for. Cometary dust gets blown off on the timescales of months. It would take a near-continuous bombardment of comets to sustain a reduced flux over the timescale of over a century. Many comets in a similar orbit would be required, which is not something we know how to obtain. So what possible explanations remained? One popular idea that was advanced was that of alien megastructures, that a civilization far ahead of humanity, technologically, was constructing an apparatus that periodically blocked a large percentage of the star's light. As the structure became more and more complete, that would increase the amount of light that was blocked. Over the past century, the fact that the light from this star had dimmed by such a significant amount could be explained by an advance in how completed the structure would be. It's a compelling, if out-of-the-box idea. Studies claimed the strange dimming could be evidence of a Dyson sphere, a hypothetical structure which could be used by an advanced civilization to harness the energy of a star. But thanks to a myriad of follow-up observations, we know that it's wrong. The reason? An object like an alien megastructure would be completely opaque to light. It would be unable to pass through it. This is equally true of things like planets, moons, or any other solid objects you can imagine. From over 19,000 images captured in recent years, in 4 different wavelength bands from blue light all the way to infrared light, we've learned that blue light is preferentially blocked in all dimming events, from the short-term flux dips to the long-term fading of the star. There's one thing known that can cause bluer light to be blocked while redder light is preferentially transmitted: dust particles that go down to at least a certain minimal size. Therefore, it must be dust. Whatever is causing the flux dips, as well as whatever's causing the long-term fading, must both have a dusty origin. But this is still a bit mysterious. After all, Tabby's star is a combination of things that we wouldn't expect to find together. It's consistent with having a large amount of circumstellar dust, which normally indicates an extremely young star still in the formative stages. The star itself is brighter, hotter, and more massive than the Sun. It gives off more than 4 times the amount of light our Sun does. The star is old, hundreds of millions of years old, burning stably on the main sequence by all accounts. In other words, the dust we see should last only months given the properties of the star itself. There must be some way for the star to replenish its dust. It's not because the star is young or still forming, and there are incredible constraints on the star having an unseen companion. It cannot all come from interstellar dust. Was a planet devoured? Is there something even more unusual afoot? The only way to know will be with more and better science on this object. But one thing's for certain, even if alien megastructures exist somewhere, they aren't here. And to find them out, there are multiple hunts for alien life currently underway. On Mars, a rover is collecting samples that may determine if life ever existed on the red planet. Probes are visiting some of our solar system's icy moons to search for signs of habitability. Astronomers are also beginning to scour the atmospheres of planets beyond our own solar system for telltale elemental cocktails that hint at alien life. And yes, we are even keeping a beady eye out for signals from any intelligent civilization that might purposefully or accidentally make contact. In our solar system, Mars is arguably the most popular destination to hunt for life at present. We know the planet was likely wet and potentially habitable billions of years ago, with seas and lakes on its surface. More recently, scientists have even found tantalizing clues that there may be liquid water on Mars still, hidden beneath the planet's southern ice cap. Currently, NASA's Perseverance rover is scooping up samples from the now dry bed of what was thought to be once a lake in a region called Jezero Crater, just to the north of the Martian equator. The goal is to collect dozens of samples and return these to Earth in the early 2030s, a mission known as Mars Sample Return, where they can be investigated in detail for signs of life. Elsewhere, a NASA spacecraft called Europa Clipper is due to launch to Europa in October, following a European spacecraft, JUICE, which launched in April 2023. Set to arrive in 2030 and 2031, the 2 spacecraft are not likely to detect life on Europa, but they will study the extent of its ocean and set the stage for a future mission that might try to burrow beneath the ice sheet, such as an ongoing NASA proposal called Europa Lander that remains on the drawing board, or fly through plumes that might be ejected from the moon's oceans into space to look for life. But according to Brittany Schmidt, an astronomer at Cornell University in New York, actually getting a machine into the ocean of one of these worlds is a 100-year problem because of the difficulties of getting through the multi-kilometers thick ice. But getting into the ice shell and interacting with liquids is something we could do more near term. Scientists are working on instruments and technologies, so we know when we get there what to do. In case you aren't quite ready to wait 100 years, then you might want to cast your gaze to other solar systems. We now know of more than 5,500 planets around other stars, known as exoplanets, and more continue to trickle in every day.
Proxima B, and so what's the story? And that it's Earth-like.
Yes, so what makes Proxima B interesting is that it's an Earth-like planet orbiting the nearest star to the sun.
If it goes as planned, the journey to Proxima B will take about 20 years, so realistically, it will be several decades before we can confirm if there is indeed life on that planet.
In an astonishing revelation, James Webb has made a breakthrough in exoplanet imaging, releasing the clearest and most detailed image of Proxima Centauri b, a potentially habitable exoplanet orbiting our nearest neighboring star, Proxima Centauri. This milestone marks a major advancement not only in our technological capabilities, but also in our quest to understand distant worlds that might harbor life. Join us as we dig deep into the unprecedented revelations of Proxima b and what it could mean for the future of exoplanet exploration. Let's start with some basics. Proxima Centauri is the nearest star system to Earth, at just 4.24 light-years away, and it's getting closer. Over the next few tens of thousands of years, it will come within 3.1 light years of us. The first planet discovered around it, Proxima b, is it at the right distance from its star to potentially support liquid water on its surface. It's firmly within its star's habitable zone. Proxima b also has an estimated mass of 1.3 times our own world, which implies that it's only about 10% larger in diameter than Earth, and is almost definitely rocky. The hope and speculation is that it might have an Earth-like atmosphere, the same raw ingredients and elements as our world, and most excitingly, perhaps even life on the surface. However, the problem is, Proxima b is a lot closer to its parent star than Earth is to the Sun. Instead of 365 days, it takes a mere 11.2 days to orbit Proxima Centauri. Its average orbital distance is just 5% of the Earth-Sun distance at 7.5 million kilometers, which means that it's got to be tidally locked to its star by now, with one roasting side, one frozen side, and an intermediate ring that's probably the most temperate portion. It also means that the sun-facing side gets ravaged with these flares frequently and from a very close distance. These flares won't entirely strip an atmosphere away, but they will absolutely destroy any sort of UV-protecting ozone layer on timescales far faster than a planet could regenerate it. So Proxima b won't have an ozone layer, which means ultraviolet, ionizing radiation can reach the surface. Because it rotates at just 9% the speed of Earth due to its orbital period and its tidal locking, its magnetic field should be far weaker than ours is, offering reduced protection against charged particles and solar winds. As far as we can tell, the surface would be vastly irradiated by potentially deadly radiation from the sun, ionizing atoms and molecules on the light side, and potentially destroying any type of chemical-based life we could create. But those difficulties for human-like life might not pose any problems at all for the kind of life that would evolve on Proxima b. Anyways, depending on what's in the atmosphere and the water on the surface, life could be an absolute cinch on this world. Winds blow from the light, hot side to the cold, dark side, providing a solid means of energy transport. The lack of protection from ionizing radiation is troubling until you realize that Proxima b itself emits extremely little ultraviolet light, owing to its low temperature. It's only during these flaring events, which occur approximately once every 2 to 3 months, that enough ultraviolet light is released to cause harm to the life it's exposed to. And it's true, even primitive UV-resistant life on the surface, like lichens or mosses, would be in trouble. But even a thin layer of protection would keep life safe. While the ozone layer won't do, there's another layer that would, in theory, perform wonderfully. The top 200 meters of an ocean. The ocean appears blue because water more readily absorbs longer wavelength, red light, than the shorter wavelength blues. Ultraviolet light is even shorter wavelength, and therefore penetrates the ocean the best. But marine life on Earth has already figured out the key adaptation, to take refuge in deeper waters when ultraviolet light is most intense. Given that these flares are clearly visible and the same side of the world always faces the sun, either organisms could adapt to be UV resistant, or they could do what every terrestrial creature does, as appropriate, take shelter when danger comes. A cave, a dark place, or even deeper depths in open water would transform a potential catastrophe into a minor inconvenience. For red dwarf stars like Proxima Centauri, their worlds have conditions that make it unlikely for life to have taken the exact same evolutionary pathway that life on Earth took. But that doesn't spell doom for life. It merely indicates that alternative pathways are required to arrive at similar outcomes. Frequent flares and excessive blasts of ultraviolet radiation may spell doom if Earth-based life were subject to those conditions. But organisms that have adapted to their environments could survive these outbursts routinely. A few solar hiccups a year should pose no problem for life forms that developed under those exact, harsh conditions. After all, on every world, it should be the organisms most robust against the adversarial conditions they face that will survive. With this possibilities, Proxima b stands as a significant milestone in the search for habitable exoplanets and the potential for extraterrestrial life. And the James Webb Space Telescope is one of the main instruments that could play a crucial role in the search. The telescope, launched in December 2021, represents one of the most advanced tools available for examining celestial bodies like Proxima b. Unlike its predecessor, the Hubble Space Telescope, which primarily observes in the visible and ultraviolet light spectra, James Webb is designed to operate predominantly in the infrared spectrum. This capability allows it to penetrate cosmic dust clouds that often obscure our view of distant objects, offering a clearer and more detailed examination of celestial phenomena. Infrared observation is particularly advantageous when studying exoplanets. For Proxima b, Webb's ability to detect infrared light enables it to capture crucial data about the planet's heat signatures and atmospheric composition, details that may be invisible to telescopes operating solely in the visible spectrum. Since its launch, James Webb has significantly advanced our understanding of Proxima b, providing insights that are both awe-inspiring and perplexing. One of the most groundbreaking revelations from the Webb telescope is the unprecedented clarity with which it has captured images of Proxima b. These images represent the sharpest view humanity has ever had of this intriguing exoplanet, revealing surface features that previous observations could not detect. For example, scientists are now able to observe a stark contrast between Proxima b's day side and night side, a significant advancement in our ability to analyze the planet's environmental conditions. The brighter appearance of the day side suggests the potential presence of reflective clouds or ice, raising intriguing questions about the planet's surface and atmospheric conditions. In contrast, the faint glows observed on the night side are a source of ongoing research and debate among astronomers. Initial hypotheses propose that this glow could be indicative of auroras, similar to the northern and southern lights seen on Earth. Given Proxima Centauri's status as a red dwarf star, known for its frequent and powerful solar flares, it is plausible that these flares interact with Proxima b's magnetic field, assuming the planet possesses one, to create this luminescent effect. This potential interaction implies the existence of an atmosphere that can effectively conduct solar wind particles, hinting at the possibility of Proxima b having a magnetic shield akin to Earth's. Such a shield would be vital for protecting the planet from harmful radiation, creating a more stable environment where life could potentially flourish. However, this is not the only explanation for the mysterious glow. Some researchers have suggested that it could be the result of volcanic activity, with active volcanoes on Proxima b potentially emitting light during the planet's nighttime. If this theory holds true, it could signify a geologically dynamic world with internal heat sources, potentially supporting subsurface life. Moreover, a more speculative theory posits that the glow could be artificial, possibly a signal from advanced alien technology. While this notion is not widely accepted within the scientific community and remains firmly in the realm of speculation, it highlights the range of possibilities that Proxima b presents. Each hypothesis, whether involving natural phenomena or intelligent design, fuels a deeper inquiry into the planet's potential for habitability. The reflective characteristics of Proxima b's day side, alongside the intriguing features noted in its nighttime observations, suggest conditions that could be conducive to life. For instance, if Proxima b has an atmosphere that effectively distributes heat, it might mitigate the extreme temperature fluctuations typically associated with tidal locking, a condition where one side of the planet constantly faces its star. This could create a temperate zone on the planet, increasing the chances of life-sustaining environments. Conversely, the threat posed by Proxima Centauri's frequent solar flares cannot be overlooked. These flares can bombard Proxima b with high levels of radiation, potentially stripping away its atmosphere over time and rendering the surface inhospitable. However, the presence of auroras, or indications of a magnetic field suggested by the observed glow, may point to a protective mechanism against such radiation. This duality raises compelling questions about the balance of conditions that could either support or hinder the possibility of life on Proxima b. The potential for volcanic activity adds another layer of complexity to the investigation of Proxima b. If active volcanoes exist, they could create environments reminiscent of Earth's hydrothermal vents, places where life thrives in complete darkness, deriving energy from the chemical processes occurring within the planet's interior. In this scenario, it is conceivable that life on Proxima b could exist not on the surface, but rather in subsurface habitats shielded from the harsh conditions of space. After all, the implications of the images captured by the James Webb Space Telescope are profound, not only because they provide new and exciting details about Proxima b, but also because they open up a plethora of questions. Is Proxima b truly a habitable world, or is it primarily a hostile environment with only a few enticing clues hinting at the possibility of life? Could the enigmatic glow on its night side be a natural occurrence, or does it indicate something more extraordinary, perhaps even extraterrestrial in nature? Future observations conducted by James Webb will be critical in addressing these inquiries. The telescope's continued monitoring of Proxima b will focus on understanding its atmospheric composition, temperature variations, and potential biosignatures. This ongoing investigation promises to deepen our understanding of not only Proxima b, but also the broader search for life beyond our planet. But while James Webb has opened a new window into Proxima b, there are still limitations and challenges. For one, Proxima Centauri's activity remains a hurdle. Its frequent flares can disrupt observations and could also strip away Proxima b's atmosphere, complicating efforts to study it in detail. Additionally, because Proxima b is tidally locked, any atmosphere it has might differ significantly from Earth's in terms of circulation and stability. The other major challenge is distance. While 4.2 light-years may be close on an astronomical scale, it's still too far to send a probe in the near future. Observations by James Webb and other ground-based telescopes will remain our primary method of study for the foreseeable future. However, technological innovations are being explored to address these challenges. One of the most promising initiatives is the Breakthrough Starshot project, a collaborative endeavor backed by prominent scientists like Stephen Hawking and funded by billionaire philanthropist Yuri Milner. Breakthrough Starshot represents a transformative approach to space exploration. The primary goal of the project is to develop an entirely new class of space probes. Small, lightweight nanoprobes equipped with light sails. These probes, while minuscule in size and mass, could achieve unprecedented speeds, potentially reaching up to 20% of the speed of light, or 0.2 c. If successful, these probes could make the journey to Proxima b, an exoplanet orbiting the star Proxima Centauri, just over 4 light-years from Earth, within 20 years of launch. This time frame would be a historic leap compared to any spacecraft launched to date, as even the fastest human-made object currently would take tens of thousands of years to reach Proxima b. The mechanics of Breakthrough Starshot's light sail technology are fascinating. The idea centers around ultralight, wafer-sized probes attached to extremely thin and durable sails. These sails are designed to capture energy from highly focused laser beams directed from Earth. The laser beams would act as the primary propulsion system, allowing the probes to rapidly accelerate to a significant fraction of light speed. This laser-driven propulsion concept leverages recent breakthroughs in photonics, the science of generating and controlling photons, typically used in optical communications, and material sciences to solve the formidable challenges of interstellar travel. The laser beams needed for Breakthrough Starshot's mission would have to be immensely powerful, with an output potentially in the gigawatt range. For comparison, a gigawatt of energy is approximately equivalent to the output of a large nuclear power plant. This level of energy would enable the lasers to accelerate the tiny probes to their target speeds over just a few minutes. The lasers would likely need to be situated in a vast array, either on the ground, possibly in a remote desert location where interference is minimal, or even in space to reduce atmospheric distortion. Placing the lasers in space could provide a clearer path for the beams, but it would also introduce significant engineering challenges and costs. An essential aspect of Breakthrough Starshot is the development of the probe's light sails, which must be ultra-thin yet robust enough to endure the high-energy laser blasts without tearing or melting. While this technology is still in its conceptual phase, recent advancements in photonics and material science have made the idea more plausible. Engineers are exploring the potential of materials such as graphene and molybdenum disulfide, which are lightweight, flexible, and durable. Graphene, a single layer of carbon atoms arranged in a two-dimensional honeycomb lattice, is incredibly strong yet lightweight, making it a leading candidate for the construction of these sails. Another promising material, molybdenum disulfide, is similarly strong and offers unique properties that might help the sails withstand the extreme thermal and structural stresses of laser propulsion. These materials represent a new frontier in material science, combining minimal weight with remarkable strength and thermal resilience. While laser-driven light sails are suitable for unmanned probes, sending humans would require more substantial propulsion systems with energy sources that can last over long distances. This is why nuclear propulsion has been revisited, with both fission and fusion methods being considered viable for interstellar travel. Nuclear fission propulsion systems harness energy through the process of splitting atomic nuclei, releasing large amounts of energy. This method has already proven useful in both terrestrial and space applications, making it a likely candidate for further development in interplanetary missions within our solar system. In space exploration, fission reactors could provide a stable and continuous energy source for ion thrusters or other electric propulsion systems, allowing a spacecraft to generate steady and reliable thrust over extended periods. For instance, ion thrusters work by electrically charging particles, such as xenon ions, and accelerating them to high speeds to produce thrust. Powered by a nuclear fission reactor, such engines could provide consistent acceleration, allowing a spacecraft to gradually achieve high velocities over time, perfect for long-duration missions. NASA and other space agencies are already investigating the use of fission reactors to power space missions. A notable example is NASA's Kilopower project, which aims to create compact, lightweight nuclear reactors designed for space. While these systems were initially intended for use on Mars or other interplanetary destinations within our solar system, the same principles could be adapted to longer-duration, deep space missions. However, to make nuclear fission a feasible option for interstellar travel, several engineering and safety challenges must be addressed. Unlike relatively short interplanetary missions, a fission-based interstellar mission would require a reactor capable of operating autonomously for decades without refueling, potentially lasting throughout a multi-generational voyage to another star system. Additionally, the fission reactor would need to remain stable and reliable despite prolonged exposure to the radiation, micrometeorite impacts, and other challenges of deep space. Autonomy is crucial, as a spacecraft traveling beyond our solar system would face significant communication delays and be largely isolated from Earth. Therefore, engineers would need to design a fission reactor that could detect and respond to potential malfunctions, adjusting its operations without any human intervention. By creating a highly automated and resilient system, it might be possible to make nuclear fission propulsion a practical option for extended interstellar missions. While nuclear fission provides one potential pathway, nuclear fusion offers even greater promise, as it could theoretically propel a spacecraft to a significant fraction of the speed of light. Fusion, the process that powers stars like our Sun, involves combining atomic nuclei at high temperatures and pressures, releasing tremendous amounts of energy in the process. In terms of energy output, fusion far surpasses fission, meaning that it could accelerate a spacecraft to much higher speeds. If achieved, fusion propulsion could open up the possibility of reaching Proxima Centauri, the closest star system to the Sun, within a human lifetime. Achieving a controlled fusion reaction on Earth has proven to be a significant scientific and engineering challenge, let alone attempting to create and maintain such a reaction in space. Nonetheless, several exciting concepts for fusion propulsion have been proposed, each utilizing different methods to attempt sustained fusion. One such concept is the fusion-driven rocket, FDR, developed by researchers aiming to use magnetized target fusion to produce thrust. In this design, plasma is compressed until it reaches the necessary temperature and pressure to achieve fusion. The fusion reaction produces a high-energy exhaust that could propel the spacecraft at much faster speeds than chemical or ion propulsion systems. The fusion-driven rocket concept is promising because it addresses some of the difficulties of achieving fusion in space by using magnetic fields to contain and compress the plasma. The idea is that a series of carefully controlled fusion pulses would produce thrust, steadily accelerating the spacecraft to velocities much faster than conventional methods. Another noteworthy design, the Daedalus project, was developed by the British Interplanetary Society in the 1970s. This ambitious concept sought to propel an uncrewed spacecraft to the vicinity of a nearby star, such as Barnard's star, using nuclear fusion. The Daedalus design involved firing small pellets of deuterium and helium-3 fuel into a reaction chamber, where they would be ignited by an electron beam to create fusion. Each fusion reaction would produce a burst of high-speed particles, creating thrust that would push the spacecraft forward. Designed as a multi-stage system, Daedalus would burn through an enormous supply of fusion fuel in each stage, gradually accelerating to about 12% of the speed of light, potentially reaching its target star in just under 50 years. Despite the ingenuity of Daedalus, the concept remains largely theoretical due to the technological hurdles that must be overcome before controlled fusion propulsion can become a reality. One major challenge is the need for a sustained, controlled fusion reaction in space. While experimental fusion reactors, such as the International Thermonuclear Experimental Reactor, are making progress on Earth, they require massive infrastructure and extremely high temperatures to sustain fusion. Creating a fusion propulsion system that can fit within the confines of a spacecraft and operate autonomously over decades is an enormous engineering feat. Furthermore, a fusion reactor for interstellar travel would require large amounts of helium-3, a rare isotope not found in abundance on Earth, but potentially available on the Moon or in the atmospheres of gas giant planets like Jupiter and Saturn. If nuclear fusion isn't powerful enough, scientists have also been exploring antimatter propulsion. Antimatter, the mirror version of ordinary matter, releases an incredible amount of energy when it comes into contact with matter, providing far more energy per kilogram than nuclear reactions. In simple terms, antimatter is composed of particles that have the same mass as their matter counterparts, but possess opposite charges. For instance, the antiparticle of an electron, known as a positron, carries a positive charge instead of a negative one. When antimatter comes into contact with regular matter, the result is a process called annihilation, where both particles are completely converted into energy. This reaction releases a staggering amount of energy, far exceeding what is produced by conventional chemical reactions and even surpassing the energy per kilogram produced by nuclear reactions. Because of this, scientists believe that antimatter could, in theory, provide the thrust needed to accelerate spacecraft to unprecedented speeds, possibly allowing travel close to 90% of the speed of light. The idea behind antimatter propulsion involves generating and storing antimatter, then carefully controlling its interactions with matter to produce a stream of high-energy particles. This high-energy release could, in turn, be harnessed to create thrust. An antimatter rocket would theoretically use the energy from matter-antimatter annihilations to drive high-velocity particles out of the back of the craft, propelling it forward at remarkable speeds. For instance, a gram of antimatter reacting with matter would release energy equivalent to an explosion of about 43 kilotons of TNT. At such a rate, even a tiny amount of antimatter would provide immense power, making it an ideal candidate for deep space missions where conventional fuel sources would be impractical. However, the prospect of antimatter propulsion comes with its own formidable challenges. The most pressing of these is the production and containment of antimatter. At present, antimatter can only be generated in extremely small quantities within particle accelerators. These massive machines can create antimatter by accelerating particles to high speeds and smashing them together, which occasionally results in the production of antimatter particles. While this process has proven that antimatter can indeed be created artificially, the quantities produced are minuscule, and the cost of production is prohibitively high. It's estimated that a single gram of antimatter could cost hundreds of billions of dollars to produce with current technology. This makes antimatter propulsion currently impractical for any large-scale application. Even if antimatter could be produced at a reasonable cost, storing it presents another considerable hurdle. Because antimatter annihilates upon contact with any matter, including the walls of any containment vessel, it cannot be stored in a regular physical container. Instead, scientists are investigating advanced containment methods using electromagnetic and magnetic fields. By creating a trap using magnetic fields, antimatter particles can be suspended in a vacuum, isolated from any contact with matter. This technology is still in its infancy, but progress is being made. One type of containment being explored is known as a penning trap, which uses a combination of electric and magnetic fields to confine charged particles. Future advancements in trap technology could make it possible to store antimatter safely for extended periods, potentially bringing antimatter propulsion a step closer to feasibility. If scientists are successful in overcoming these challenges, antimatter propulsion could open the door to remarkable advancements in space exploration. By enabling spacecraft to travel at a significant fraction of the speed of light, antimatter propulsion could make interstellar travel possible within human timescales. This means we might be able to send probes to distant star systems or even consider manned missions to nearby stars. Such advancements would have profound implications for humanity's understanding of the universe and could be the key to answering some of the biggest questions in astrophysics, such as the potential for life on exoplanets and the nature of distant celestial objects. In the coming decades, ongoing research in particle physics, advancements in particle accelerator technologies, and breakthroughs in containment methods may bring antimatter propulsion closer to reality. Although still a distant dream, scientists are optimistic that the incredible energy potential of antimatter could one day be harnessed for space travel. Should antimatter propulsion become feasible, it would represent one of the most groundbreaking achievements in human history, transforming the way we think about our place in the cosmos and potentially ushering in a new era of interstellar exploration. Another significant note: the distance and harshness of interstellar space require spacecraft to operate autonomously and with resilience against radiation and micrometeoroids. Thus, robotic probes equipped with AI and constructed using nanotechnology would be essential for a mission to Proxima b. AI would be critical for an interstellar mission, as communication delays make real-time control from Earth impractical. Probes and, eventually, crewed spacecraft would need onboard systems capable of autonomous decision-making for navigation, repairs, data collection, and even crisis management. NASA and private companies like SpaceX are investing heavily in AI for autonomous space systems. with developments in machine learning models capable of adapting to unforeseen circumstances in space. In addition, nanotechnology also could play a major role in reducing the mass and increasing the durability of interstellar probes. Lightweight materials made from carbon nanotubes and other nanostructures offer high strength-to-weight ratios, essential for light sail and other high-speed propulsion technologies. Nanomaterials also exhibit unique properties for radiation shielding, which would be crucial for both protecting sensitive electronics and ensuring the safety of human crews on such long journeys. Nanotechnology also supports the development of smart materials that can self-heal or adapt to damage from micrometeoroids or cosmic rays. Incorporating nanotechnology into spacecraft could reduce the need for redundant systems, making the vehicle lighter, more energy efficient, and better equipped for the journey to Proxima b. And for human missions, advanced life support systems are essential, considering that any journey would likely take decades even with the fastest propulsion systems. Current life support technologies on the International Space Station, also known as ISS, involve recycling water and oxygen, but interstellar travel demands innovations in closed-loop systems and biological support. NASA has been researching closed-loop life support systems that can recycle water, air, and waste with minimal resupply. Future systems might integrate algae or other forms of bioengineering to continuously replenish oxygen and food supplies. Bioregenerative systems, which mimic Earth's ecosystems, could offer a sustainable solution for interstellar travel, supporting human crews for extended periods without resupply from Earth. One of the ways to mitigate the challenges of long-duration space travel is to develop hibernation or cryogenic sleep technologies. Placing humans in a state of low metabolic activity could reduce the need for resources and prevent the psychological stresses of prolonged confinement. NASA has been exploring this concept for Mars missions, using techniques that reduce body temperature and metabolic rate. Although cryogenic sleep is still experimental, advances in medical technology and cryogenics could enable long-term hibernation for interstellar travelers, reducing life support requirements and making human missions to Proxima b more practical. Transmitting data back to Earth across interstellar distances is another major challenge. Traditional radio signals would become weaker over such long distances, so more advanced communication technologies are required. One promising solution is laser communication. Unlike radio waves, laser-based transmissions can achieve higher speeds and capacities, allowing for efficient data transfer across long distances. By directing a concentrated laser beam from an interstellar probe back to Earth, data can travel at significantly higher rates than with conventional radio signals. Organizations like NASA and ESA are already developing laser communication systems for deep space missions, and advancements in this technology could potentially support communication with probes traveling to distant exoplanets, such as Proxima b. Quantum communication represents another potential breakthrough in interstellar communication. This technology uses the phenomenon of quantum entanglement, which could theoretically enable instantaneous data transfer across vast distances. Though still in the early stages of development and not yet practical for interstellar use, research in quantum communication is progressing quickly. If these advancements continue, quantum communication could eventually provide real-time data transmission, opening new possibilities for communicating with interstellar probes or even crewed missions, significantly enhancing humanity's ability to explore deep space. Moreover, maintaining power for probes or crewed spacecraft over decades requires power sources that are both reliable and durable. Radioisotope thermoelectric generators, which convert heat from decaying radioactive material into electricity, have been used in space for decades, including on Voyager, Cassini, and the Mars rovers. For interstellar missions, radioisotope thermoelectric generators could be optimized with higher efficiency materials and longer-lasting isotopes, providing a steady power source for long-duration flights. On the other hand, if fusion technology becomes viable for propulsion, it could also serve as a sustainable power source for onboard systems, providing energy for life support, communication, and scientific equipment. Fusion reactors are still in development, but compact, sustainable reactors would be crucial for manned missions to Proxima b, as they offer energy density far exceeding current technologies. After all, sending probes and humans to Proxima b is one of the most challenging endeavors humanity could undertake. Although the technology required for such a journey does not yet exist, ongoing research in areas like light sail propulsion, nuclear fusion, antimatter propulsion, AI, nanotechnology, closed-loop life support, hibernation, and advanced communication shows promising potential. As these technologies develop, they may converge into an interstellar mission within the coming century. With breakthroughs in these fields, humanity may one day reach Proxima b, opening the door to exploring and perhaps even colonizing worlds beyond our solar system. The journey to Proxima b represents not only a technical challenge, but also a testament to human curiosity and our drive to explore the unknown.